introduce Mr. Sashikumar Menon. Mr. Menon is the Director of Gratias Solutions with career spanning 4 decades.
Let's start with the question, what is profitability? Profitability can be defined as a measure how much profit does a business make. That's profitability, of course. Now, here we are not talking about any business. We are talking about manufacturing business. So how can we attain profitability in the manufacturing business? How to increase profitability in manufacturing business? Of course, reduce the process cost. That's the only option. How to reduce the process cost? Increase productivity. Yes, all knows that. How to increase productivity? Manufacturing process involves lots of factors. It's not only, several things are there, material, machining, your transportation, your quality control, lots of processes are in manufacturing process. But one of the processes is machining cost, which is the topic of the session. So we'll discuss on that. So how to reduce the machining cost? That's a million-dollar question. Everybody wants to decrease the machining cost. So the basic thing how to reduce the machining cost is increase the material removal rate, high MRR. Now the machining process, everybody knows it involves the following major factors. The machine, of course, you should have a machine for that. Second is the work holding. Third, the cutting tool. Fourth, the tool holding, programming, chip evacuation. All these things are very important. For a profitable or a successful machining process, you should have a good machine. You should have the work holding device should be good. The cutting tool should be suitable for your application. Tool holding should be suitable. You should have a good programming strategy. And the chip evacuation, the chips should be removed from the cutting edge. And apart from all these things, one major factor is this, the man. Despite having all these things, if the man who switches on the machine is not, then everything goes at toss. The operations in machining are roughing, semi-finishing, and finishing. Generally, semi-finishing does not say in between process, so sometimes it overlaps with roughing and finishing also. So we'll not be discussing about semi-finishing in this session. We'll be talking more about roughing and finishing. So to improve productivity means how fast we are doing these operations, how fast we do the roughing, how fast we do the semi-finishing, how fast we do the finishing. That means how fast we are removing the material, high MRR. That's what we are. Everything depends on that. Your productivity, your profitability in machining depends on how fast you are removing you're doing these operations, thereby you are increasing your material removal rate. Okay. Now, we have traditional machining strategies, especially let's see the productivity and how we can increase the productivity in roughing in traditional methods. Can we increase the depth of cut? Yes, of course. Can we increase the feet per tooth or feet per revolution, feet per tooth in milling and feet per revolution in drilling and turning? Of course, we can do that. Can we increase the step over, which we call as pitch or AE or whatever it is? Can we increase that? Yes, of course, we can do that. Increase the cutting speed. In traditional roughing, I'll say no, maybe. Because you can increase the depth of cut, you can increase the feet per revolution, you can increase the step over, everything is there. Then why should you increase the cutting speed over there? Because in roughing, if you increase the cutting speed, does really, you have got a high depth of cut and you've got a high feed rate. Now you're going to increase your cutting speed also. That really does not match. So I'll generally say increasing cutting speed in roughing is not a very good strategy. Now, roughing, you've got so many ways of increasing your productivity. But what about finishing? Traditional finishing methods. Can we increase the depth of cut? No. Why? Because the depth of cut is already predetermined in your roughing or semi-finishing operations. And thereby increasing the depth of a cut, you're not going to gain anything. Either whatever left of material in the roughing or semi-finishing applications, only that you have to remove in finishing. So there's no point of increasing depth of cut there. So increase the feet per revolution? No, because increasing the feet per revolution or feet per tooth is going to damage your surface finish. your surface will get affected. Now, what is left? Increase step over? Big no. Because again, especially in ball nose cutters, if you increase the step over of the pitch, your scallop height is going to be high. That means your surface finish is bad. When the scallop heights are high, with the RI value or RZ value, whatever values will be very high in those cases. So there's no case of increasing step over also in finishing applications. Now, increase cutting speed. Yes or maybe. Yes, because traditional finishing applications you can have small depth of cuts, and also you can increase the cutting speed. But you have to have certain norms on that. Then only like your cutting tool and all those things should help you in doing that. So increase the cutting speed in finishing is okay. In many ways it is okay. Productivity in finishing in traditional method is a little bit difficult because you have to follow the same depth of whatever the metal left has to be cut, whatever feet per revolution you cannot increase that. You cannot increase the step over. Maybe you can increase cutting speed. So only if you increase the productivity in finishing also, then only your metal cutting process becomes a profitable process. So how to increase productivity in finishing? That is with new strategies. First of all, what we are going to discuss here is increase cutting speed. I earlier said maybe, in conventional or traditional I said maybe. But here with the new strategies, increase the cutting speed is a big yes. And that is known as high-speed machining. So we can to increase the productivity in finishing, we can increase the cutting speeds and have a good profitable solution. Second is increase step over. That also is possible with the new strategies called as barrel milling. Since that's not a subject of this discussion, I'll be talking about high-speed machining only. Barrel machining, maybe we can talk later or something like that. So let us define what is high-speed machining, or HSM. It is called as HSM, high-speed machining. There are lots of definitions of high-speed machining. Some people say it is high MRR. Yes, of course, it is high MRR because that is the ultimate aim. What I feel is HSM is a machining method which achieve to lesser cycle time by increasing the cutting speed. Let's see why I'm saying that. High VC means high RPM, of course. So high RPM already, when your cutting speed is higher, your RPM definitely is going to increase. So the base is VC. High RPM means high table feed, even if the feed per tooth is less. Generally in milling for finishing applications, you have to go for a low feed per tooth, maybe as low as 0.05, 0.03 like that. When your RPM increases, according to the formula, Fz into Z into RPM is BF. That BF is the table feed. The table feed will increase. That means your high MRR. So high VF, that is table feed, means lesser cycle time and high MRR. So that means HSM can be defined as machining with high VC. So the VC is the basics of everything. If you want to increase the cutting RPM, you have to have a high VC. When the RPM is increased, your table feed increases. If your table feed increases, your MRR increases. So the basic is can say HSM can be defined as machining with high VC. Advantages of HSM. At elevated VC, the cutting speed, the cutting forces at the cutting edge will be reduced. When the cutting edge touches the workpiece material, when the cutting edge of the tool touches the workpiece material. Actually, if you see, before going to that, we always say metal cutting, metal cutting, metal cutting. Actually, we are not cutting metal. We are shearing the metal. See, cutting means take a knife and put it 90 degree, cut a tomato or potato. We are not doing like that on a VMC or HMC or a turning center. The cutting tool touches the workpiece material and it moves. During that movement, it is shearing the material in the form of chips. So, when the cutting edge touches the material, the huge cutting forces will be produced. At elevated VC, when the cutting speed is high, the cutting force at the cutting edge will be reduced. Why? Because High VC speeds up the plastic deformation of the material. If you want to shear the material, you cannot just shear the material like that. It has to get softened. There should be a process called plastic formation of the material. That means it reaches a certain temperature and it becomes, because if you want to say forge steel, you have to heat it to make it soft. Similarly, here also, if we want to shear the chip away from the workpiece material, the workpiece material should get heated up. And how this is getting heated up? It is because of the rotational forces. That is depending upon your VC, on your cutting speed, how much RPM you are giving. Higher the RPM or the higher the cutting speed, higher the heat generated. So your plastic deformation of the material will be quicker in the case of high-speed machining. Second is less cutting force means good surface finish, because the forces are less and the material is getting sheared off very easily. So due to the faster plastic deformation, so there is less cutting force over there, so it is easy. So your surface, the surface finish also will increase, and your feed per tooth also is less. At elevated, we see the height and high table feed. The chips are cut very fast. See, when you have a high feed rate, high table feed and high cutting speed, the chips are generated very quickly, which helps to carry away the heat generated very quickly. There will be heat generated at the cutting edge. Where should the heat go? The heat cannot go to the cutting tool. The heat cannot go to the workpiece material. So where should the heat go? The heat should go into the chips. The general concept is 80% of the heat produced while machining should be carried away by the chips. 10% can go to the cutting tool, 10% can go to the workpiece material, not more than that. If it goes more than that, if your cutting tool is taking more heat, your tool life goes down. If your workpiece material is taking more heat, there can be structural damages for the workpiece because of the high heat. So heat will be there. Heat has to be, when the process is there, some heat will go to everywhere. It will go to the workpiece material, it will go to the cutting tools, but it should not be too high. All the heat generated, 80% of it should be carried away by the chips. Because chips are going away, so nothing is remaining there. So it will not affect the cutting tool material, or it will not affect the workpiece material. So ensure that apart from high-speed machining, in any machining process, it should be ensured that 80% of the chips, 80% of the heat was carried away by the chips. So at elevated BC and high table feeds, chips are cut so fast that it won't give time for the heat to go into the cutting tool or the workpiece material. Okay. Hence, there is very little tendency for the heat generated during the process to be transferred to the tool, which means better tool life. When there is less heat to the tool, it means your tool is getting, the wear out on the tool will be less. That means your tool life will increase by HSM method. And finally, very important part, less cutting force also means less load on the spindle, which means better spindle life. Of course, the machine is running at very high RPM, that also matters. But apart from that, if you consider this factor alone, less cutting forces also means less load on the spindle, which means better spindle life. Now, cutting tools for HSM. Carbide, you can use carbide for HSM. Both the substrate and coating should have the qualities of high wear resistance and hot hardness. The tool should be having high wear resistance because your cutting speeds are very high, the heat is very high. It should have also the property of hot hardness. Both the substrate and the coating should have the qualities of high wear resistance and hot hardness. Second is the most suitable material for HSM is PCBN, polycrystalline boron nitride. This is a second hardest material after diamond. This is a hardest material invented by man and the second hardest material after diamond. So this is a very apt solution for machining PCB, especially for hard materials. Substrate with cubic boron nitride and a ceramic binder. See, any substrate of a cutting tool should have a cutting element and a binder. For example, if you take carbide, it is tungsten carbide and cobalt. Tungsten carbide acts as the thing which cuts, and cobalt acts as a thing which holds the tungsten molecules together. So generally we call carbide as cemented carbide. The reason is just like two bricks are held with a cement, the two molecules of tungsten carbide is held with cobalt, which is a cement inside the substrate. So that is why we call it a cemented carbide. Similarly in PCBN also, the cutting function is done by the part of by cubic boron nitride, and these things should be held together, and that is done by ceramic. Now, if you see, both cubic boron nitride and ceramic binders have highly wear resistant and have hot hardness. So that means cobalt won't retain its hardness or capability beyond a certain temperature, say around generally the temperature at the normal cutting temperature at the cutting edge in normal other than HSM is around 800 degrees centigrade. Cobalt will not resist beyond 800 degrees centigrade. It will start to melt or whatever it is. But ceramic is a very highly wear resistant and having hot hardness. So that will resist high temperatures. So both are highly wear resistant and have high hot hardness. So PCBN or polycrystalline boron nitride will work much better at higher cutting speeds because both the cutting element and the binding element both are highly wear resistant and have high hot hardness. PCBN is highly suitable for machining hardened steels above 45 HRC and HRSA materials. HRSA materials are heat resistant superalloys. Very difficult to machine materials like titanium, nickel, columbium, whatever are used in aerospace and rockets and all those things. They are very difficult to machine. PCBN can give you a better solution over there. Especially, but hardened steel, PCBN is one of the best solutions for machining hardened steel with high cutting speeds. Then coming, the third one is PCD, that is polycrystalline diamond, which is suitable for, which is also substrate to synthetic diamond particles with metallic binder. Diamond, you know, is the hardest substance in the world. Very suitable for machining aluminum at extremely high VC. Extremely high V means you can think around 2000, 5000, so not 5000, 2000, 3000 cutting speeds. You can machine probably even 5000 is possible. I'm not sure. At that high cutting speeds, you can machine, you can use PCD for machining aluminum. Very high cutting speeds. Very long tool life. PCD will give you very long tool life while machining aluminum. Normally, cutting tool people does not like PCD because tool life is so long and your business is so low. And even trials also. As an application engineer, if you go for a trial for this PCD, you have to wait for months for a result. So generally, so now tool holding, very, very important. Tool holding can break or make HSM. It's a very important fact. It can make or break HSM. Not only HSM, any machine goes, but especially in HSM because your RPMs are very high. So it is very important that the tool holding system should be very good. The runout should be as close as possible to zero. Of course, zero is not possible, but your cutting edge should have the runout as close as possible to zero. That's possible. But bringing the runout to say 2 microns, 3 microns is possible with a good tool holding systems. But this is very important. The runout should be as close as possible to zero. Another thing is good balancing. The tool holder should be extremely balanced. It should be extremely important that it should have good balancing. What happens? Anything that rotates will experience centrifugal forces. You know, the centrifugal forces, when you rotate something like this, the force that pulls the material, the substance away from the center, that's called a centrifugal force. While rotating, everything will have experience centrifugal force.
Sorry to interrupt. We are running short of time.
Yeah, I'll just complete it. So anything that rotates will experience centrifugal forces. Higher the rotation, higher will be the centrifugal forces. So if the holder is not well balanced, especially during HSM, the centrifugal forces will drag the tool holder, which means cutting is not balanced. Unbalanced cutting will reduce the tool life, spoil the surface finish, and harm the spindle. So you should have a very good tool holding system also. So HSM requirements are sturdy, high quality machines, work holding device with sufficient clamping force, wear resistant cutting tools with property of hot hardness, well balanced tool holders with good run out, reliable CAM software, coolant system for efficient chip evacuation. I'm saying that reduce RPM of the machine to achieve higher profitability. Now, all of you might be thinking, has this guy gone mad? We are talking about high-speed machining and he's saying to reduce RPM. Lesser the RPM of the machine, higher will be the profitability. So, are you confused? Probably. RPM is not just rotations per minute. It is also rupees per minute of the machine. HSM technique will help you to reduce the RPM of the machine. Thank you.